We're now going to move on. Yes.
So about the FBI and spying on packets, but it doesn't make sense legally to for them to for governments to have this ability. Because as a citizen, if you're not doing doing everything in the boxes of law, then you have nothing to worry about. But on the other hand, what they are trying to do is prevent some attacks or whatever.
Yes. So the question is, doesn't it make sense for government agencies to have access to traffic to try to stop crime? And I think, it does make a lot of sense to do that. I think the question is really those concerns I brought up earlier, but what is the cost? Which is, do you trust that your government will always use it good? In general, I think many, probably a majority of people in the United States do some things that are illegal. Whether it's running red lights or, not paying their taxes or something like that. And so if you have a government that sees anything, it could choose to sort of selectively prosecute almost anybody when it wants to. So it's sort of a huge amount of power that you give somebody if you let them see everything. And so you're sort of choosing, when you give a government the capacity to see all the traffic, you're choosing to sort of let it, if it chooses, to target almost any person at any time as a criminal. And so, there's a question, do you trust your government? I think the government in this country has been pretty good. And since the reform of the CIA and FBI in the 70s, I think it's done a pretty good job. Some people may beg to differ, given sort of the issues of the Trump campaign last year. In other countries, people may have more concerns. The other concern is a real one, which is, once you create this capability for law enforcement, are there other people who can use it? So if you have wiretapping capability and you have unencrypted traffic in your router, could the router manufacturer put something into SNP? So for example, the US government has really said, we don't want to allow routers from Huawei or ZTE into the United States because we don't trust that this equipment manufactured in China doesn't have surveillance backdoors built in that will sniff on traffic and send reports to the Chinese government of what's happening. I have no idea what's happening, but when you have unencrypted traffic and you have that surveillance capability, you can't always control exactly who uses it. There was a comment over here.
I was going to say, not every citizen agrees that the law is passed, and that can be problematic if you want to do things that are banned. Because we don't really have direct control over what laws are passed as citizens.
Right. We don't have direct control. We do get to vote for people, which is very indirect control. Yes. Right? For example, even academic records. There are laws on how your records are sold. They're called FERPA. They control how student records are stored. And I can bet that not every person, including me, stores your data on encrypted, encrypts their laptop hard drive so that if somebody stole their laptop, they couldn't see your grades because it's cumbersome. And so there's lots of laws that are good laws and good intentions that people just haven't gotten around to, or it's too cumbersome to follow the rules yet. And so once you make surveillance possible, you make it possible to sort of go after anybody like that for something very small if you want to. Other thoughts? Okay. So our next topic is virtualization. This relates to cloud computing and really the security issues that come up in cloud computing. What I want to do is talk about what virtualization is. We touched on it briefly earlier this semester, and I want to go into more detail now, and then talk about some of the security risks that come up in virtualization. And what's interesting is a lot of the topics here is actually research that's been done at UW-Madison or by people who were here. So first off, we'll talk about the basics of virtualization. Our normal picture of no virtualization is you've got hardware, you have an operating system on top of it, you have your user mode processes running on top of that operating system, and the operating system totally controls the physical hardware, the hard disk, the graphics, the keyboard, the mouse, the CPU, and memory. In full virtualization, we run what's called a hypervisor, which is a software layer that creates virtual hardware. It looks just like a regular processor. It looks like a regular network card, a regular hard disk, a regular mouse and keyboard. But instead of actually talking to the device, it's a software implementation. And that software implementation can sort of choose to either emulate the device completely. So if you're sending a network packet, it might not ever talk to your network card. It might respond internally. Or it can choose to share the existing hardware between different virtual machines. This allows us to create multiple virtual machines on top of this virtual hardware where they each run their own operating system. So that is the picture in the middle where we have fully virtual hardware. We now have two operating systems that are sort of don't know about each other. They don't share anything. They're completely separated. They run their own set of processes. And then the final case is what's called para-virtualization. And this says, you know, emulating an Intel E1000 network card is a big hassle. So what I want to do is I am going to modify the operating system to know that it's running in a virtual machine. And I'm going to replace those device drivers for real physical devices with device drivers that know about these virtual devices that are a lot more efficient. So this requires modifying your operating system here, but it's a lot simpler for the hypervisor than emulating real hardware, and it can potentially be a lot faster because you can build a better interface. So the operating system in this picture is called a guest operating system, and it runs inside a virtual machine, which is the virtual hardware that the hypervisor creates. Questions on this picture? Yes. So full virtualization says we are going to present an exact copy of some real hardware. We're going to make it look like you have an E1000 network card, NVIDIA GPU, a Microsoft mouse, and a 102-key keyboard. So any existing device drivers you have for those physical devices will actually work in this fully virtualized system. In a para-virtual system, we don't attempt to actually copy real hardware. What we do instead is write device drivers for virtual devices instead. So we'll write a special device driver for a virtual network card, which will do something like a system call into the hypervisor to send a packet. So it basically is the difference of whether we fully emulate the hardware or we modify the operating system to know about virtualization and do something simpler. So another difference is what's called a type 1 or type 2 hypervisor. So a type 1 is what I showed before, or it's on the right, where the hypervisor talks directly to the hardware. This means the hypervisor has all the features an operating system has of memory management and has device drivers to talk to hardware. Type 2 is what's shown in the middle now, where there's a host operating system. And the idea here is that operating systems have device drivers, they have memory management, they have scheduling. Why recreate this in the hypervisor? We're just going to have the hypervisor talk to a host operating system. So if it needs memory, it'll go to the OS and allocate memory. If it wants to send a packet, it'll sort of get the packet from the guest operating system and then call the device drivers or the networking code on the host to send a packet. If you want to write to the hard disk, the same thing happens. We talk to the host OS. So this means that you're running your whole regular operating system, and then part of it is this piece that virtualizes the hardware. And this is what is done in Microsoft Windows with Hyper-V and in Linux with the KVM hypervisor. So a little bit of history here. So virtualization was first created around 1970, I'll get to it in a minute, by people frustrated with IBM because they didn't like IBM operating systems, but they had to use them for some things. They wanted to do time sharing, which wasn't possible. Yes? Unfortunately, I have a choice of recording slides or being able to go backwards. And so I can certainly draw pictures on the board. Sure. So the question is, what is the host OS responsibilities? Okay, can people read that? So this is the picture. The question is, what is the host OS responsibility? So you can see in this picture, the host OS responsibility sort of sits between the hypervisor and the hardware. And what I'm implying in this picture is that it is really responsible for sort of resource management and for abstracting the hardware. So the host OS will do memory allocation. If you want to decide how much memory to give to your virtual machines here, host OS has policies for doing that. The same way it has policies when you run multiple processes, how much memory each thing gets. For example, swapping and memory allocation. Similarly, host operating systems, if an operating system extracts hardware. So when you have a physical network card with some device interface to it, and you're writing device registers, that is presented through a device driver as sort of some generic network device that sends packets through a procedure call. And so rather, that means the hypervisor, when it wants to access physical hardware, calls through the host operating system and uses its features to access the hardware. So when it sends a packet, it'll call the host operating system to send a packet. The host operating system calls a driver, which talks to hardware. When it wants to allocate memory, it asks the host operating system for memory. The host operating system can then allocate the memory, create page tables, and tell the hypervisor. When you want to do scheduling, when you want to switch between these, the host OS does scheduling, so the host OS can sort of use its scheduler to interrupt one of these and say it's time to switch and start running the other one. So it's really moving, saying the hypervisor's job is really emulating this hardware, but the policies and the management of the hardware stays in the host operating system. In a type 1 system, the hypervisor does all of that.
Virtualization, you have the drivers within the guest operating system.
Yeah. Right, so in paravirtualization, you have drivers here. In full virtualization, you have real device drivers that sort of ship out of the box for some particular device. And then you have a device emulator. So in this case, your guest operating system would call this device driver like an Intel E1000. It'll sort of do what it does doing memory mapped I/O. The device emulator and the hypervisor will see this device I/O and say, oh, the guest OS is trying to send a packet. Let me get that packet and send it to the host operating system, which will then send it through a real driver here into the hardware. Is that more clear? Okay. So originally it was sort of invented because IBM only had batch processing where you could run things for a long period. People wanted time sharing. So somebody said, well, we'll build we can build a virtual machine and run the batch operating system in one virtual machine, and we'll run time sharing in another. We don't have to use IBM's awful operating system anymore. So it became very popular on sort of mainframe computers in the early 1970s. There's a ton of research in the area. But then it sort of died away until 1999. And what happened is computers got small, and if you wanted a different operating system, you just buy a different computer for $1,000. And so there was no reason to use virtual machines when your hardware was cheap. It was great when you had $1 million machine and you wanted 2 operating systems, but not so great at small. So what changed in 1999 was that a Stanford professor named Mendel Rosenblum and a bunch of his students, including this guy named Ed Bugnon, they have been researching how to do high-speed processor simulation for computer architecture. So they wanted to emulate, for example, what a MIPS processor does so they could add new features and sort of see how it performed. And they developed a technique called binary translation. And what this says is we're going to take a set of instructions from some binary, and we are going to translate those into a set of native instructions that execute quickly. So they would take like 10 MIPS instructions, translate them into 10 x86 instructions or 20 x86 instructions, and execute them very quickly. The previous approach was take one MIPS instruction, execute it slowly, go to the next MIPS instruction, execute it slowly, so you would get a very, very slow system. And this meant that you could execute binaries for some other processor almost at full speed. This is used by WoW64. If you want to run x86 binaries on ARM, on Windows, this is used. Apple used this technology when it moved from Power processors into x86 processors. But they released a product called VMware Workstation, and the target was, one thing they did is they figured out how to virtualize x86. And if you want to learn why that's important, take CS537 or 736, but it's very difficult, and it took Stanford PhDs to figure it out. And the reason people like this is, one, it let you run multiple operating systems on your desktop. For a long time, Microsoft licenses said, if you pre-install Windows on every single machine that you sell, we will sell it to you for like half the price than if you get to choose which machines you install it on. Which meant that companies like Dell would never sell you something without Windows because it would make everything else cost a lot more. So with this, you could get your machine with Windows, put on VMware, run Linux in a virtual machine. It also was great because if you had some reason to run an older version of Windows, like maybe you needed Windows 3.1, maybe you needed OS2, you could run both your normal operating system as a host OS and run a guest operating system with whatever version you wanted. So this is very popular also for testing. You know, you can test your application here on different platforms. So there's lots of great uses. So this product really sort of created a renaissance in virtualization that turned into cloud computing we're using today. So it's sort of a pretty amazing story of academic research. So the next big step was 2003. This was sort of the first open source virtual machine monitor that was popular. It was developed by a group in Cambridge. It's called Zen and the Art of Virtualization with the paper. I was there when it was presented. At this conference, I actually got the Best Paper Award, although they got 10 years later, they got the Test of Time for being the most influential paper at the conference. So I think it was well deserved. But what this work did is it sort of developed the idea of para-virtualization, which I mentioned before. And so they said, you know, we think it's a lot easier to modify Linux as an open source operating system than it is to virtualize x86. So we're going to modify Linux a little bit, build a very simple hypervisor. This is a type 1 hypervisor, which means there's no guest OS. And we're going to use that for access. So this was widely used. This was adopted by Amazon when they launched Amazon the Elastic Compute Cloud EC2. So this was the hypervisor used to create cloud computing. It was later, the students who did this started a company called ZenWorks, I think, that was bought by Citrix a while ago. And so Zen is sort of a very widely used virtual machine monitor. Although now there's something built into Linux called KVM, which is becoming more popular. Amazon and Google both use KVM for their virtualization. So what is virtualization good for? So one, legacy support. You know, if you want to run Windows 10, but you have an application that still needs Windows 2000 because it's not compatible, you can run Windows 2000. Development is great. If you want to test your code on some other operating system you're not using, it's a great way to do that. Another really popular case is what's called server consolidation. And the idea is that there are many applications, particularly on Windows, that expect that they are the only thing running on an operating system. So for example, if you start up SQL Server, it more or less says how much physical memory is in the system, and then it'll say, great, I want it all, and allocate all your memory. So this means if you want to run 2 copies of SQL Server, they kind of conflict because they both want all the memory. But your database might not actually need a whole machine. It might not be that busy. Similarly, if you run Microsoft Exchange Server, it's going to say I want all the memory, and the Microsoft Web Server wants all the memory too. So what you can do instead is you can run 5 virtual machines on one host and take each of these, what used to be a physical server running a separate application, and consolidate them all into one bigger, slightly bigger machine. This means that as an operator, you have fewer physical machines to manage. It takes less space. You have flexibility of how many resources this machine has. If you need a new virtual machine, you can create one in seconds. And so this is a great way to sort of give each of your applications a dedicated operating system with its own special configuration and its own resources, but then run it all on a single machine. So after that, people started looking at cloud computing infrastructure as a service. Amazon said, you know, what if we sort of create virtual machines and then let our customers run their operating system? So this became AWS EC2, where Amazon manages a whole bunch of physical machines. You give them a virtual disk, and they will run it on their hardware and sell it to you for 6 cents an hour or something like that. And another thing people started looking at or looked at is using this for sandboxing. This is the example we mentioned before, where you want to run some risky code, and so you want to run it in a separate virtual machine so that it can't corrupt other things going on. So as an example, if you're using Amazon Lambdas, which is a popular programming model now called function as a service, you write Python functions or JavaScript functions. Each of these from different users runs in a different virtual machine to sort of isolate them from each other so that one customer can't sort of interact with the code or data of another customer. So it lets you have sort of securely share hardware between multiple users. Okay, so do people see what virtual machines are good for, believe that they're useful? And so what we want to look at then is how secure are they really? You know, how much of this sort of, when I say they totally separate operating systems, do they actually accomplish that? Actually, before I get to that, I'm going to get to something else, which is how these are used as a research tool. So one of the things that researchers want to do is they want to study malware. right? So if there is some botnet infecting thousands of machines, as a researcher, you'd like to install that botnet software, run it, see how it, see what it does, see how it behaves, figure out who it's communicating with, figure out how to stop it and circumvent it. So if you do it on a real machine, it's hard to control what it's doing because it's hard to sort of stop the machine and look at it very closely. It also has the risk that that real machine might corrupt all the other machines in your network. So malware researchers like to run things in virtual machines instead because they can do things like pause the virtual machine and look at the state of memory. They can look at what's on disk without the operating system getting in the way. So if your malware infects the operating system and blocks certain functionality, you can get around it through the virtual machine, through the hypervisor. So this means you sort of reduce the harm to yourself by running malware, and it allows you to sort of inspect things at a much deeper level because you can see the full contents of memory, the full contents of this virtual disk you've created. However, malware writers aren't stupid. They know this is going on. And so what malware writers have tried to do is to say, let's figure out, are we running in a virtual machine? If we're running in a virtual machine, let's act benign and not do anything and just shut ourselves off. If we're running on real hardware, then we will actually do our malicious thing. And so they will have code, they will try to detect, are you running in a virtual machine or not? So this raises the question of, can you conceal the fact that you're running in a virtual machine from some piece of malware that wants to know? And as you would expect, given this class, the answer is no. So one reason is paravirtualization. Paravirtualization, you're running different device drivers. So anybody who can look at the list of device drivers can see you're running the wrong device drivers for real hardware. The other thing is that virtual hardware doesn't always behave exactly the same. There's some instructions that might do slightly different things. Some locations in memory might be different. There are, for example, VMware has, there's a particular instruction I'll get to that behaves very differently in VMware because VMware uses this instruction to communicate between the hypervisor and the operating system quickly. And this is called the red pill method of detection. The other thing is that some things are slower in a virtual machine because we're virtualizing hardware. So if you can measure time, you can measure how slow things are, and you can see, oh, this is something slower, I know I'm in a virtual machine. So there's a paper by Garfinkel, Simpson Garfinkel, basically, Cal Garfinkel, saying that really you can't not be detected if you're running a virtual machine. So here's an example of how you would detect old VMware. You would load this particular instruction into EAX. You then do the in instruction, which is IO instruction, and then you would compare the resulting EDX. And VMware used this to communicate, and so if you did this on VMware, you would see a particular value in EDX, this virtual machine number. If you were on real hardware, you get a processor exception. So any malware writer who's running in the kernel could issue this instruction, detect if they're on a physical or VMware, and then behave differently, shut themselves off, clean themselves out of memory, so that nobody could watch what they were doing. So this is sort of a arms race in a way of trying to sort of thwart detection. So this is still ongoing as a vulnerability. Okay, so we will stop there for today, and next week we'll pick up with more attacks on virtualization, so a couple minutes early. If you still haven't picked up your exam, I have exams here to return.